Welcome back to Math 130. Today we're going to be talking about logarithms and logarithmic functions. When we've been talking about equations in the past, we've talked about how we can solve for either y or x. Well, with an exponential function like we covered in the last section, the question becomes, how do you solve for that x? And the answer is a logarithm. And in fact, the exponent x is the logarithm of the number y to the base b. So let's look at how we write that. If y equals b to the x, then the logarithm x equals log base b of y. So let's look closely at how those are related. The exponent is the logarithm. It moves to the left. X equals everything else. The base b moves down here as a subscript following the word log, and y moves out here to the end. And the way we read that logarithm is x equals the log base b of y. And here are the terms that we use for each part of that equation. X is the logarithm, which used to be the exponent. B is still the base, just as it was over here. And y is now called the argument. I don't know why, don't argue with me. So on the left we have the exponential form, and on the right we have the logarithmic form of the same equation. Here's an example. You're aware that 3 squared equals 9. This equation is written in the exponential form. So let's write it in the logarithmic form. The exponent x is equal to 2. Okay, the exponent is 2. We write the log, and I usually write that in cursive. Not necessary, but that's the way I do it. Base 3 of 9. So basically, when you read this, when you're looking at it, you say, well, what exponent of 3 will give me 9? So 3 to the what equals 9? Well, that what is 2. Right there. 2 equals the log base 3 of 9. Here's another example. You know that 10 cubed equals 1,000. All right, so if we convert that to logarithmic form, the exponent 3 is equal to the log base 10 of 1,000. Because you are asking yourself, what exponent of 10 will give me 1,000? And the answer is, we can also take this in the reverse direction. If 4 equals the log base 2 of 16, that's the same as saying 2 to the 4th equals 16, which we know to be true. And if we write it strictly in the form we have above, we would write 16 equals 2 to the 4th. Completely equivalent, just mirrored. Let's get a little bit fancy. What would the log base 5 of 1/25 be? The answer is -2, because if we rewrite that in exponential form, we would get 5 to the -2 equals 1/25, which you know to be true because you know how to deal with negative exponents. All right, shall we confuse things a little bit more? When we have your exponential form and your logarithmic form written like this, it's easy to see how everything moves from one to the other. Now, if we wanted to rewrite the exponential form in function notation, it looks like we're going to be varying x, that it is our independent variable, so we would write it this way. Right? However, the logarithmic form, it looks like we're solving for x, which is exactly what we're doing, and we are making y change to see what happens. So in order to write this as function notation, we would either have to write it this way, or we would have to switch our x and our y, writing the logarithmic form as this, and the functional notation as the function of x equals the log base b of x. And actually, this is exactly how we do it, although most of the time, when you're dealing with logs, you do not use the function notation, or at least we're not going to be doing that. We're going to be doing it this way. This is what you will see in your book. Y equals log base b of x. Don't get hung up with which one's x and which one's y. Look for the pattern. This is still the base, and the x now is located within the log. That means this is now the argument, and here is your exponent. Because even written this way, it is still true that 2 equals the log base 3 of 9, because there's the base, there's the exponent, and that is equal to the argument of 9. Let's look at the graph of a logarithmic function now. We look at y equals the log base 2 of x. Making a t-table for a logarithmic function is a little tricky. I'm going to start with the number 1. So I ask myself, what exponent of 2 will give me 1? And the answer is 0. What about the number 2? The log base 2 of 2 is, well, what exponent of 2 gives me 2? That would be 1. If I were to do the log base 2 of 3, what power of 2 gives me 3? I don't know. Let's try something else. Let's try instead 4. So the log base 2 of 4, what power of 2 gives me 4? Well, that's 2. That one worked nicely. Then I have to go a good bit further until I find a number for which I can easily find the log in my head. The log base 2 of 8 is 3, because 2 to the third gives me 8. So let's see what happens if we try to find 0, or the log base 2 of 0. What does that equal? 2 to the what equals 0? Nothing. And by that I don't mean 0. I mean there is no number that you can use as an exponent of 2 to get 0. It just doesn't happen. Likewise, we cannot do negative x's because there is no power of a positive 2 that will give you a negative number. So instead, we're going to have to resort to some fractions. Let's try 1/2. The log base 2 of 1/2 equals, well, that would be 2 to the negative 1. And then if we do 1/4, log base 2 of 1/4, well, that would be 2 to the negative 2 that equals 1/4. And for 1/8, that would be 2 to the negative 3rd. There are the points that we have figured out, and we can graph them just like this. Now, I chose these values of x because I knew what was going on with a logarithmic function, because I've had years of experience. How can you deal with it? Use your calculator. Now, when I was in high school and college, we had to use tables of logarithms because scientific calculators were just coming on the scene, so we had to page through literally pages of logarithms listed to find the ones we wanted. So be thankful for that superpowered calculator you have in your hands and use it. For comparison, I have graphed y equals 2 to the x, the exponential form, over to the left in red. So do you notice anything about those two graphs? If you look very closely, you can see that they are mirrored over the line y equals x. They are, in effect, inverse functions of each other. And that's where I'm going to stop this video. I will see you in part B shortly.